So how does this relate to KB and Ka? Since we have a situation where most of the acids and bases, there are very few that are considered to be strong, almost all of them are weak, they are going to have Ka and Kb values that are small. They're going to be less than 1 because they are not going anywhere near completion. They are mostly staying in their molecular form rather than coming apart. So the equilibrium is shifted very much to the left. These numbers that come from the products are going to be small. This is still going to be very nearly the same as the original concentration. So if we have a 0.1 molar solution and the pH is 2.2, we'd like to know what are all these values. All right, let's start because there's a lot of stuff in number 10. If we look at number 10, we can start and think about what we did before, which was to say that my concentration of hydronium ions should be equal to 10 raised to the negative pH. They've given us the pH, so I'll just say it's 10 to the negative 2.20. Use my calculator, and I'm going to go with just 2 sig figs now. 6.3 times 10 to the negative third. All right, what else is true about this? Well, because these are products from when this falls apart, that means I also know that that is the same concentration for whatever the anion was. So I got 2 of them already. They're both this number. What about HA? What is it? Well, they told me what it started at. It was 0.100 molar. However, we just came up with this, right? This is the amount that was created. So some of this has fallen apart. How much? Well, that much. So I'm going to have to subtract 0.0063. Well, you can see with the sig fig thing here going on, that we're going to have to just round that back and say that it's 0.094 molar. So you can see some of it fell apart, but not very much. So I found this, I have found this, I have found this, and now I need Ka. Okay, that's fine. What was the definition? Well, it was the products, which would be this hydronium ion, and whatever the anion concentration was, over the concentration of the acid that has not fallen apart. I'll just put these numbers in, 6.3 times 10 to the negative third, and because they're both the same thing, I'll have to square that, and then divide by the 0.094. And because this is an equilibrium constant, we're not going to worry about the units. Go through on your calculator. Whoops, why did I write a 7? That's supposed to be a 4. 4.2 times 10 to the negative fourth. Okay, so there we go. We have found that. Now we have another definition. Degree of ionization is the ratio of the hydronium ion concentration to the original, not this one that we just figured out, which is how much was left, but the original, and it's usually expressed as a percentage ionization in this way. All right, well, we have those numbers, so we can just use them. Percent ionization then, you're going to go ahead and put the 6.3 times 10 to the negative third, which was the concentration of hydronium ion, over the original concentration of HA, and change it into a percentage. When you run that through your calculator, you should get 6.3%. So we now know that if we had 100 of these, We would not, only 6 of them would actually fall apart. The others are going to remain exactly as they were, as a molecule. So that is our percent ionization for this solution. Now here is something really odd. Weak acids will exhibit a higher degree of ionization as they are diluted. That is a very strange thing to contemplate. So we have to sort of explain why that would happen. Think about Le Chatelier. That is what you should be doing in this case. And I'm going to go ahead and write something down before we get to 11, really. But it is going to be part of 11 to just try to understand this. I have some sort of weak acid, and I have put it in with water. It's going to go into an equilibrium. It's going to form the anion, right? And it's also going to form hydronium ions. I don't know why I put those concentration symbols there, but it's all right. You get the idea. At equilibrium, I'm going to have a situation where this value K is these products. And then the only reactant we put is HA, because this is supposed to be a liquid. It's not aqueous like these others. It gets ignored in this type of equation. Now consider, when you are adding water to this, you are adding a reactant as far as Le Chatelier is concerned. That is going to be a shift. It's going to change the equilibrium. So if we have Le Chatelier happily showing up, and I say, oh, I'm raising the amount of this, it's going to push the whole thing this direction. That means that these are going to go up, and this is going to go down. So both of these are going to go up. This is going to go down. That means that K is going to go up. That means more of this weak acid is dissociated. It's a new situation because of what just happened. So the more water you add, the less concentrated it gets, and the higher the percent ionization. So even a weak acid like nitrous acid can make, here's 45% dissociation if your concentration is really, really low, because these are already 0.02. Oh, that's very small.